Let's look at nitric acid and see if we can determine why it is such a powerful acidic molecule. Here is the structure for nitric acid. All the molecules involved are sp2 hybridized, but for the oxygen ones, when they form the sp2 hybridization, they do it with different patterns. Let's just take a look at the molecular orbital diagrams involved. We'll start with nitrogen. Remember, nitrogen, for all of them that we're discussing, we have 2 s electrons and then the 2 p electron orbitals. We have 2 of them here for nitrogen, and then the p orbitals have a single electron, and what can happen is the s orbital can combine with 2 of the p orbitals. So we're combining together 3 atomic orbitals, 1 s and 2 p's, to form equivalent, that is energy equivalent, 3 molecular orbitals, the sp2 orbitals. And we have 1 p orbital that did not hybridize. So for the sp2 orbitals, the block diagram is very simple. It's this, and of course, remember the geometry here. The nitrogen has the sp2 orbitals, they're 120 degrees apart. Like this, and then the p orbital at that single electron, that is perpendicular to this flat plane. Okay, now let's consider this oxygen. We see the nitrogen can form 1, 2 sigma bonds, which it does with this oxygen and with the hydroxyl oxygen, and it has a lone p electron that it can use to participate in this pi double bond with this oxygen. So remember, oxygen does have a single p electron or a single pi electron available to form this double bond. But here, this bond has an arrow on it indicating a coordinate bond. Let's just see how that happens. So to do that, we're now going to consider the block orbital diagram for oxygen. So again, 2s has a pair of electrons, and then the p orbitals are like this. One of the p orbitals does have an electron pair. Now, one thing that can happen is that these electrons that each occupy a p orbital can pair up to leave an empty p orbital. This is the more energetically favorable state, but we can have this. Where these have paired up to share a single orbital, and we have an empty p orbital. This is the more favorable configuration energy-wise, so it takes some energy to do this, but as a result of doing this, if it allows us to form an extra chemical bond, then that energy from the bond more than offsets the energy that it takes to pair these electrons and forcing them to occupy a single orbital. And indeed, notice this p orbital is empty, but notice this nitrogen, the nitrogen, has this lone electron pair for one of the sp2 orbitals. So what can happen is the nitrogen can donate both electrons for this empty p orbital, and that kind of situation, remember from general chemistry, that's called a coordinate bond, and that is what this arrow indicates. Okay, now let's look at the other oxygens. Like we said, all the atoms here, all the molecules are sp2 hybridized, but they do it in different ways. Let's consider the hydroxyl oxygen. We've examined this before in previous videos, but let's just do it quickly here. Again, the orbital diagram for oxygen. The two s electrons and the p electrons. And we imagine, again, taking one s orbital and combining it with two of the p orbitals, and the p orbitals that we're going to use have a single electron in them. And again, we're going to form three equivalent sp2 molecular orbitals. And an unhybridized p orbital is left over, and it has a lone pair of electrons. So the hydroxyl oxygen can form two sigma bonds. It does, one with nitrogen, one with oxygen. It has this lone electron pair, and of course these are the sp2 molecular orbitals. So this is the sp2 lone pair electrons. Here are the lone pi or the lone p orbital electrons. And again, remember the geometry. We could have an oxygen nucleus with an sp2 orbital 120 degrees apart, the sp2 orbitals, single electron, the lone electron pair, then perpendicular to that, above and below the oxygen atom, we would have a pair of p orbital electrons, or we just call them quite often just pi electrons. So that is how the hydroxyl oxygen is sp2 hybridized. Now, for this one, the one with the double bond, again, sp2 hybridized, so we take a single s orbital, combine it with two p orbitals, but this time when we do it, one of the p orbitals that we use has the electron pair. Let's say we use this one. So again, we get the three equivalent sp2 molecular orbitals, and we have a p orbital left over that was not hybridized. These are the sp2 orbitals. Like this. So we have lone electron pairs, two of them, here and here. They're both sp2 electrons. And then we have this, where it can form a sigma bond with the nitrogen, and a pi electron, a p orbital electron. Remember we said the nitrogen has a single p orbital electron also left over, so they can share, each one can share their p orbital electrons and form the pi bond. So those are the hybridization patterns. They're all sp2 hybridized, but the oxygens, as you can see, form their sp2 hybridizations in different ways. But that then is sort of an overview of the structure of nitric acid. Now, you can see that these are all sp2 electrons, and these are sp2 electrons, but the hydroxyl oxygen does have a lone pair of pi electrons, and we have this pi bond right here. So we have an electron in the pi bond from the oxygen atom, another electron in this pi bond from the nitrogen atom, and then adjacent to the nitrogen, where we have these overlapping p orbitals, we have oxygen with its p orbital and these lone pair of pi electrons. So if you've watched the other videos, you can probably guess what's coming up next, and we will show you, but there will be a complication here because of this coordinate bond. So let's draw this nitric acid. And what you can imagine happening, as we discussed in the previous videos, the oxygen and the nitrogen, they're sharing pi electrons. Suppose the oxygen keeps both of them for itself. In other words, it swipes it from the nitrogen. So nitrogen lost its electron, but here we have these pi electrons. These can swoop in and pair with nitrogen. So you can have the double bond reestablished, but in this case now the oxygen is putting up both of the electrons to form that double bond. So the resonance structure, or the Lewis structure, would be like this. This pi bond no longer exists because oxygen kept both of the electrons that were being shared, so it now has a lone pair of pi electrons and a negative charge, because it stole an electron from nitrogen. Then we have the positive, or not the positive, but the double bond with the hydroxyl group. But since oxygen put up both electrons to form that bond, it has a positive charge. And we have this Lewis structure, or this resonance structure. This is just oxygen with a lone pair of pi electrons here and a negative charge. This one has a positive charge. Separation of charges is not ideal, particularly when you have an electronegative atom like oxygen carrying a positive charge, but it is permissible. So that is a valid Lewis structure for nitric acid. And that's what we're trying to do, is see different ways that we can shuffle the pi electrons about to form different Lewis structures. Hopefully you've watched the previous videos and you see that's what resonance, or p orbital electron delocalization, is all about. We're just doing exactly what we did in the previous 8 or 9 videos now. So we're kind of building on that knowledge. But now, here, let's look at this. Originally, this nitrogen and this oxygen were sharing pi electrons. This had a pi electron, and this had a pi electron that they were sharing in that pi bond. Well, suppose that nitrogen kept or once you have this has its lone pair of pi electrons here. Suppose nitrogen takes its electron back, plus the electron that oxygen originally had. So then it would have its electron back, plus the electron that it stole from oxygen. But when it acquires that extra electron, the one that it stole from this oxygen keeps that extra electron. See, this is where it's going to get complicated now because of this coordinate bond here that we're trying to explain, and a lot of textbooks don't have this. So again, what we did originally was there was each nitrogen and each oxygen put a pi electron that they shared in that bond. Oxygen ends up keeping both of them. This now donates both electrons to form the double bond. This has a negative charge. This has a positive charge. Now, suppose that nitrogen takes back its electron plus the electron that was originally oxygen's. But as soon as it does that, this oxygen right here takes that extra electron that originally belonged to oxygen. So in other words, we're sharing two electrons here. Oxygen keeps them both. Now imagine nitrogen keeps them both. But as soon as it does that, this oxygen swipes from nitrogen the extra electron that it took from that oxygen atom. So then it would be like this. Now, this oxygen has the extra electron, so we can no longer have a covalent bond. Remember how the covalent bond was formed. This was oxygen with this normal set of electrons. These paired up. We had the empty p orbital and a pair of sp2 electrons from nitrogen filled that empty p orbital, forming that coordinate bond. Well, now, if this oxygen gets the electron that was originally belonged to that one, then there's going to be an electron in here now, and therefore you can't form the coordinate bond anymore. That has to be an empty orbital. So what will happen is this oxygen now has a negative charge, and it forms a normal sigma bond with nitrogen, just like this one did. Same thing, except this one, when it's lost its electron to this oxygen, it no longer has an extra electron. It no longer has a negative charge, so it has a normal orbital diagram. It can do this just like this oxygen originally did, have an empty p orbital, and now the coordinate bond points down with this oxygen. So we have this. And notice these two different structures here are symmetrical. An arrow going to an oxygen atom, an arrow going to an oxygen atom. A negatively charged oxygen atom, a negatively charged oxygen atom. This molecule here would just simply be this one turned over. So these are symmetrical. Now, once that happens, here we have this oxygen that acquired an extra electron from this one, and it's in the lone, it's in a pi orbital, a p orbital, just like it was with this one. So that means here then, what can happen is that, remember, this oxygen originally had a lone pair of pi electrons, but they came in to form this double bond. Well, they can go back to this one, and now these lone pair of pi electrons can come in to form the double bond. So we would have this Lewis structure. Nitrogen, coordinate bond with this oxygen. This is putting up both electrons, knowing that would give it a positive charge, but a negative charge to start with. So we have double bond, oxygen with no charge on it. And this did have a positive charge, but now it's getting both of its electrons back. It's a single bond and no charge on that oxygen. So now we have this compound, or this form, this canonical form for nitric acid. It's the same. Here, 1, 2, 3, 4 different canonical forms. We get them all together here. There's 3. 1, 2, 3. And can we get them all together? Yes, there's the 4th one. So there are 4 different canonical structures that we can draw for nitric acid. 2 of them have symmetry. So that when these are all reasonable structures, so this would lead us to believe that nitric acid, with a fairly decent resonance system, would be an inert molecule. What motivation would it have to lose that proton when it is already, it looks like, pretty decently stabilized through this resonance system? To understand that, then, what we'll have to do is say, well, if it's like this, if it does lose the proton, you form this, what would be the resonance structure of the nitrate anion? If this right here has a superior resonance system that is even better than this system, then nitric acid would be motivated, if you will, to shed that proton. So what we'll have to do in the next video is very carefully examine the resonance system for nitrate and then come back and compare it to the resonance system for nitric acid when it can't get all these together at once. There. The resonance system for nitric acid when it still retains the proton. Compare this resonance system to what it would be for the nitrate ion when nitric acid does lose the proton. And this video is already much too long. We will have to consider that in the next video. Again, a reminder, the playlist for all the videos is at the website digital-university.org.